Hi everybody, welcome to tonight's lab lecture. I hope your evening is going well. It's nice and sunny out. I hope you got to go out and enjoy the sun. For today's lab lecture, we are going to be covering two topics that we don't really get to explore in much detail in this class. And those topics are osmosis dialysis, which are generally the same thing, just from different perspectives, and also nuclear chemistry, which is not something that we generally have time to cover at all in Chem 121. So we have a lab assignment that goes over these things. Just like the conversation in the chat right now is describing, since we do cover the osmosis part in Chapter 8, that will definitely be tested on the both the quiz, Exam 2, and the final. The radioactivity stuff may be put in some questions in the final if I need to add those questions. So yeah, lab content can show up on exams and assessments, so you should definitely know and understand the content in the labs. But the primary focus of those assessments is always going to be the lecture material. So let me go to this screen, which should have nothing on it. I'm in the wrong window, so give me a second. So I can put this on the screen now. Boop. So here's lab worksheet number 4. You will see that there is the lab worksheet in the Google Sheet. There's also some videos that I would like you to watch. The videos will have questions that you need to answer, kind of like with the observations lab. But also you'll be collecting some data off of them, particularly in the osmosis lab, where a reaction will be, well, it's not really a reaction, a experiment will be done to show the effects of how stuff moves around in the solution. So if you click on here, you can get that documentation, which will show you all of the stuff. But I'm going to hide that for now because we're going to talk a little bit about these topics in detail. So the first thing we're going to talk about is osmosis and dialysis. And the way that we're going to do that is we're going to talk about solutions. And I need a different color that'll show up here. There we go. All right. So all right, so that was the worst line ever. I got to turn my tablet a little bit. There we go. All right, so in Chapter 8, which we're going to start next week, we're going to talk about solutions. And what a solution is just a mixture of stuff. And so that stuff might be a liquid, which I'm going to just label as water, because all the solutions that we're going to be working with in general are going to be water. And then some sort of stuff that you add to it, which is called the solute. The solute is a small amount of stuff that you put into a solvent, such as water. Now, for this demonstration right here, I'm going to assume that the solute is food coloring, because food coloring is probably something that everybody has worked with. And if you drop food coloring into water, and you observe it initially, it looks kind of like this. Here's my little droplet. It's in the container, and it's just there. But if you let it spread out over time, it will naturally do something like this. It will become less concentrated, but it will then fill the entire container. So it'll be really dark when you first put it in, but then it will gradually spread out and it will become less dark because now it occupies the entire space. And so the word that we use for this is called mixing. When you allow a solute and a solvent to mix together, they mix completely, and you get a homogeneous solution eventually, provided that the solute is completely soluble. Other examples of this would be things like you put salt in the water, and then once you mix the water, the salt will dissolve, and then the entirety of the water will taste salty. For instance, if you wanted to prepare pasta. Now, this is a property of all solutions. They just mix, because molecules move around randomly, and eventually they will randomly occupy every corner of the solution. But what we're going to do now is we're going to do this. So I'm going to erase my diagram here. We're going to make a new one. And we're going to change our container so that there's this barrier in the way. And actually, I should do a different color for the barrier. But I want it to show up, so let's do that. Okay. You can't tell that that's different, because I can't tell that that's different. Let's do this. That's still not great. That's much better. Okay. So now our container has this barrier in the middle. And so this right here is what I'm going to call a semi-permeable membrane. Now, what this means is a membrane is just a barrier that separates two parts of something. So, for example, cells have cell membranes, and the membrane around a cell prevents the outside stuff from mixing in with the inside stuff, because maybe that's not what you want. You don't want your contents of your cell to be dispersed and distributed randomly throughout the body, for instance. We want our nucleus to be where it is, we want the mitochondria to be where it is, and etc. Now I'm going to put my water back in here. And the water will just fill both sides of the membrane. Now, if I put some solute in here, like this, then what will happen is it will slowly fill the entirety of the side that it is on. But it might not go through the membrane. In fact, that's what the word semi-permeable means. Something is permeable if other substances can pass through it. But if it's semi-permeable, then only certain substances can pass through. And that's the substances that are allowed to pass through is dictated by the nature of the membrane. So, for example, we have several synthetic substances. We're going to use one in the video that you'll watch called a dialysis bag. And it allows specific objects to go through as long as they are under a certain size. If they're too big, like the molecules are too big, the molar mass is too high, then they can't pass through. But if they're small enough, they can pass through. Now, water is very small. Water is just this, H2O. It has a very low molar mass. And so it can pass through most membranes, provided that the pore size is not incredibly tiny. Large molecules, like, say, dye, might not be able to do that. It depends on the membrane that we're using. And for this example, we're going to assume that it can't. Now, in order to make this make sense, I'm going to actually add a small amount of dye to this side so that there's just a little bit that you can see here. And we're going to call the left side the more concentrated side. We're going to call the left side the less concentrated side. And in both of these sides is water. So the space that's in here that isn't blue is water. So water is on both sides. Now, because the barrier is semi-permeable, and because solutions want to mix on their own, what will happen is that the solutions will try to mix. Now, in this case, the dye can't move through the barrier, so it's stuck on that side, but the solution will still behave in such a way that it will attempt to get to a completely homogeneous state if it can. And what ends up happening here is that the water that's inside my container will move in a direction such that the concentrations will equalize. Now, if I have something that is low in concentration and I add water to it, so like say I put the water level up to here, this dye would spread out further and it would get less concentrated. But if I did the opposite and I made the water go down like that, then whatever dye is in here would be compressed into a smaller space and it would be more concentrated. Likewise, on the other side, if the water went up, it would be less concentrated, and if it went down, it would be more concentrated. So in order for both of these sides to have the same concentration, I got to get water from the right side to go on the left side. So this volume goes up and it becomes more dilute on the left side. And on the right side, the water goes down and that side becomes more concentrated. Now, because water can pass through the semipermeable membrane, what it does is it moves through in this direction. Now, some water does go back and forth. It will go in both directions because it's semipermeable and the molecules are moving around randomly. But the overall flow of water will be towards the left side, and the end result, and I have to get the eraser out for this, is that, well, you don't puncture the container or the membrane. The overall result is that the water flowing from right to left here causes this side to go up and this side to go down. And so all this stuff that I'm erasing off the top there now ends up, oops, that's the eraser, now ends up down here. And then all the stuff that's down here now has to spread out into this area up at the top, so I'm going to erase some of it and move it up here. And this process will happen until one of two things happens. One, both sides have the same concentration of solute, which is the dye in this case. Ooh, that was a really bad Y. There we go. I don't know what's with my handwriting today. It's just terrible. And so if this happens, the water will keep flowing until both sides have the same concentration, and then it stops because the solution is now properly mixed. Everything has the same concentration. It's homogeneous. The other thing that can happen is that the pressure, we'll call it the weight, of the water column gets too big for mixing to continue. Now, what do I mean by the water column? So I'm going to grab another color here. This right here is the water column. And so because that water is a column and is subject to gravity, it is going to push down in this direction. That push of the water's mass is going to be counteracted by the force of water moving through the barrier. At some point, we will reach equilibrium, and either one of these conditions will be true. Either everything will become equal in concentration, or the column is just too big and it can't push more water. Regardless of whatever happened, the overall effect is that water is moving from one side to the other more than the reverse direction. And so we're going to call this process osmosis. Osmosis is the movement of water from an area of low concentration to high concentration. And it's important to note that this definition is relative to the solute. Because we don't really think of water as having a concentration. Water is just kind of there. It's the background thing that we don't care about in our solutions. Usually we care about the other thing that's added. So when water moves through a semipermeable membrane, from a low concentration to a high concentration, we call that osmosis. And I should actually put that down here so that you have that. Through a semipermeable. I gotta move my tablet here. Membrane. And the membrane's important because if the membrane isn't there, then it's just mixing, and water will just mix. That's not osmosis. Now, where does this biologically happen? This happens in your cells all the time. For instance, if you eat a lot of salty food, then the concentration of salt ions in your bloodstream, because the salt gets absorbed through your intestines, in your bloodstream, you have a higher concentration of ions from the salt that you ate relative to the concentration of ions that are in the cells, because the cells have ions because they need those ions to do chemistry and biochemistry and stuff like that. If you have too much salt in your blood stream, then what ends up happening is that the bloodstream exerts a pressure on the cells. And the cells then have water move out of them. And that water causes you to get dehydrated. And so this is actually where the term blood pressure comes from. If you eat too much salt, your blood pressure goes up because water gets forced out of them due to osmosis. Because the water is trying to move water outside so that the concentration of the cells and the bloodstream are equal. If you drink too much water, the opposite problem happens, and your bloodstream has too few ions in it relative to your cells, and then water tries to move into your cells. And both of these are not ideal. You want to have an equilibrium so that water moves in the appropriate places where it needs to, and you don't suddenly dehydrate and shrivel your cells, or then expand them with too much water and then they pop. So osmosis is the force that governs how water behaves, and it's always relative to the concentrations in and out of a solution. Now, what about dialysis? Dialysis is actually the same process except with a solute. So what I'm going to do is we're going to scroll. Oh, I don't have enough space, so we're going to erase this. And we'll draw another container. And this time I'm going to put like a little bag in it. So here's my bag, which I've tied at both ends. And inside, I'm going to put a solute. So here's my solute. And then I'm going to put that bag in the water. Now, if osmosis occurs, then the water will move from low concentration to high concentration, just like we said. And it will go through the semipermeable membrane. Now, in the chat, what I want you to do is tell me which direction the water is going to move if the bag is a semipermeable membrane. Now, there is some water inside the bag because the solution is as it is. So will water move into the bag or will it move out of the bag primarily? Because we know both are going to happen, but which one will be primary? Where will the water go if osmosis occurs? Good, the water should go inside the bag. So we could indicate that by going, whoop, here's where our water will flow. It will move in this direction primarily. Now, dialysis is the same thing with solutes. And I'm going to leave a blank here. because we're going to fill that in just a second. Now, if I have my solute in there, and it's going to move through the barrier, what's the logical direction it would move? Would it be moving from low concentration to high, or high to low, relative to the solute? So where would the honey go? Or sorry, I'm saying honey because that's what we use when we do this in person. We're going to use a different solution in the video because I couldn't find a video with honey. But where would the purple solute go? Would it go in or out of the bag? Or would it just stay there if dialysis occurs? It would go out. That's right. And it kind of has to because there's no honey on the outside, right? So, if honey moves in this direction, then relative to the solute, which again is the purple stuff that I've drawn here, I keep saying honey, I apologize. The solute is going to move from high concentration to low concentration. In other words, what's happening in this scenario here is that the stuff that's in there is trying to mix. It's trying to make everything have equal concentration everywhere. On the outside, I have very low concentration of honey. In fact, it's 0. There's nothing here. On the inside, I have a very high concentration of honey. In order for this to mix, even though the bag is in the way, the honey's got to move out and the water's got to move in. If the bag wasn't there, this would be no problem. The honey would just fill the container, everything would mix, we'd have a homogeneous solution. The bag just slows the process down. The act of the honey moving through the barrier is dialysis, and the act of water moving through the barrier is osmosis. And the direction is governed based on this mixing principle. Now, if I were to put something else on the outside, we'll do this we'll pick this color. If I were to put something else on the outside, it might move too. Which direction would this orange-yellow stuff go? Would it go in or out of the bag? We'll call this solute 2. So where would the yellow stuff go? It would go into the bag. Very good. And the reason for that is, again, everything wants to mix homogeneously. Now, there is one thing to note. And that is, if the semipermeable membrane has pores that are too small, then some particles cannot pass. So in the case up here, if we chose a bag that had very large pores, everything could pass through it, and then eventually these things would all mix together, just slowly. And so dialysis would occur for the solute and solute number 2, and osmosis would occur for water. But if I chose a membrane that filtered out one over the other, for example, let's suppose that solute number 2 is very big, and that solute number 1 is small. I don't know what I just did there. I made a line. Can I get rid of that? Yeah. If this is the case, and the bag restricts things that are very big, then this doesn't happen. The yellow stuff can't get in here. but the purple one will still be able to move. So dialysis may occur, or it might not, depending on the size of the particles. And in the video that I give you, there's going to be 3 different molecules and then water. And you'll be able to identify, did something move through from one side to the other based on the test that they do. And I don't want to spoil it because I'll just give away all the answers. But there will be a chemical test to see if solutes move in and out. And that test may require a test strip, or it might just be visual. You'll see what happens, and you'll have to read the documentation to get all of that information. And then for water, water is actually a really easy test. What we do is, in order to see if water has moved into or out of the bag, you weigh the bag before and after osmosis. And so if you put the bag in a balance and it says, oh, it weighs 8 grams, and then you put the bag into the solution and then you weigh it after 20 minutes, and now you will see, oh, it weighs 9 grams now. Well, how much solute did it lose? It probably lost a small amount if that moved out. But it certainly didn't lose a gram or half a gram, because you would see it. In fact, most of the stuff that's in there is not actually solute, it's the mass of the bag. But if it gained a gram of water, the water must have gone in, and you can see that osmosis happened. Okay? That's the osmosis experiment. So on the video, you're going to watch a technician do this experiment. He's going to prepare the bag, put a sample into the bag, tie it shut, weigh it before he puts it in the water, and then he's going to put it in the water. Then he's going to add some other chemicals in various places so that you can see what happens. And then I'm going to ask you questions about, did you observe this process for this substance, and then tell me how you know. And all of the chemical tests and information that is in there is written in the documentation. So if you don't know how iodine and starch work, that's okay. It's in the documentation. It'll tell you, oh, when they mix together, it turns blue. If you've never seen like a glucose test strip, it tells you that. It will say, oh, it turns this color. All right, that's the dialysis lab. Any questions about that? Let me know in the chat. We'll continue on in just a second. All right, so I'm going to clear the screen. Oh, I don't know why that came back. There we go. The next thing we're going to talk about is the radioactivity worksheet. For radioactivity, I'm going to give you another video that shows the effects of 3 different types of radiation, and that these forms are things that you probably aren't aware of. So that's what we're going to discuss today, what these things are. So there are 3 types of radioactive particles that the video is going to explore, and they use the Greek characters alpha, beta, and gamma. The first thing I'm going to talk about for alpha radiation is that if alpha radiation is generated, what is created is a helium nucleus. In other words, that would be helium. Excuse me, I got to drink some water here. But specifically, it's just the nucleus. So that means that there is no electrons on it. Because it's helium, its atomic number is 2. And the specific helium isotope that is generated has 2 neutrons with it. So if you have a radioactive particle, it is shooting out these helium nuclei from its nucleus. So in other words, if I was to draw a picture, and this is my nucleus, then out would come a helium nucleus, which has 2 protons and 2 neutrons. And this would be alpha. For beta radiation, beta radiation is just electrons. But very importantly, the beta radiation comes from the nucleus. This is why it's called nuclear radioactivity. So all the electrons on the outside in the electron cloud don't do anything in this process. The electrons instead come out of the nucleus. And you might be asking yourself, how the heck is that possible? And we'll talk about that in a second. Now the symbology used for this is the letter E with a little minus on it, which you've probably seen me refer to before. That's just the shorthand for electron. But if I want to put this mass information in here to help us figure out what's going on, and that will be important in a little bit, electrons effectively have a mass of 0 AMU, which we talked about in Chapter 2, or Chapter 3, I believe. And then down here for the atomic number of an electron, that's really not a thing that exists in terms of number of protons. But what we're going to write instead is we're going to say that it has the charge of -1 protons. So this is the symbology for an electron. And then the last form of radioactivity, this is probably the easiest one. Gamma radiation is just photons of light. And these photons are very high in energy. And the symbol that we use for this is, well, it's just light. So it doesn't have a mass and it doesn't have a charge to it. And there is no letter for light, so we just write a gamma symbol again. And again, this comes out of the nucleus as well. Now, generally speaking, only one of these things will happen at a time. And in almost every isotope that I can think of, there is one predominant form of that, although other options may exist, but they're just rare. So for any given nuclear process, you're going to identify which one of these is happening based on its effects. And the video is going to show you how to do that. The primary ways to determine this are how to detect radiation in terms of distance and penetration. Some of these radioactive particles do not go very far. They're essentially harmless unless you ingest them. Others go quite far, and they can be dangerous even if you keep your distance. Penetration refers to how far through something can they travel and still remain reactive. Some of these particles are blocked by very simple things. For example, alpha particles can be blocked by paper. If you have a sheet of paper between you and the detector, or you and the source, the particles don't go through. They hit the paper and they react. Other particles, however, go straight through the paper. And so the video is going to clarify that in more detail. Because it's going to show a guy with a bunch of different sources. He'll say, okay, this is alpha. Look at the detector. See how it responds to me moving it closer and farther. And then he'll tell you how far away the effective distance is. Now, this stuff up here is going to be important for some of the questions. Let me see if I can do this. Sometimes this just doesn't work. There we go. Okay, so we don't want that. what we're going to use this information now is to try and predict what's going on in the form of a nuclear reaction. So I'm going to just pick uranium because everybody knows about uranium. Uranium has an atomic number of 92, which you can see on the periodic table. It's element number 92. And a particular isotope of uranium would have some number of neutrons in it. I'm going to use uranium-238 because this is a known reaction that I am familiar with, because I worked with uranium-238 as a graduate student. Or undergraduate student, sorry. If this undergoes alpha decay, then what's going to come out is a helium nucleus from the core of the uranium nucleus. But in doing this, I have to make sure that whatever I started with and whatever I end with over here obey the law of conservation of mass. So I can't create protons out of nowhere. So I can't just spit out helium nuclei from a nucleus and then nothing happens to it. So what ends up happening is that I look at the numbers for the atomic number and I have to compare them together. Because whatever this is that goes in this box here is going to be the difference. So if I had 92 protons and I shot out a helium nucleus, which was 2 protons, how many protons are left for whatever this thing is? Type it in the chat how many protons it is, and then look up on the periodic table what element that is. Because that's what we're going to write in the box. Because, as you should recall, the number of protons on my atom determines its identity and what symbol we should write. So what number goes in the box for the number of protons, and then what symbol should I write? Good, so the number is 90. So I'm going to write that down for my atomic number in here. What element is element 90? Because I got to write a symbol, but I can't do this, right? Because uranium is not number 90, it's number 92. So what symbol should I type in? Or not type in, but write in. You get to do the typing. And thorium is exactly right. Very good. Now, the last thing is we got to fill in this top number, and it follows the same principle. Whatever the mass number was before has to equal the mass number after. Well, if I lost 4, what should go in the blank? And that's correct, 234. So what this is called a nuclear reaction, because the nucleus is changing. In a chemical reaction, when you do chemistry, we're only moving around entire whole atoms and not changing their identity. So when I mix hydrogen and oxygen to create water, all the hydrogens stay hydrogen and all the oxygens stay oxygen. And the water is just the combination and creation of bonds between those atoms. But in nuclear chemistry, we actually change the nucleus, and so the identity changes. Okay, so that's why this is different. So this was an example that had an alpha reaction. Let's look at one that has a beta reaction. And I got to pick an element for this. I'm going to pick, let's do lead. I don't know if lead actually does this, but we'll just choose it. I'm going to pick 208, and lead is element number 82. And we're going to suppose that it ejects an electron from its nucleus. And we said before, up at the top, that an electron has a -1 for its atomic number, in quotes, and has no mass. So now, if I'm going to add that to whatever is left over, what number, first of all, should go in the box? What number is going to be the difference between these two? What number should I put here? And then, what element is that? Now be careful, because if I put 81 here, does 81 plus -1 equal 82? That's the trick here, because it's an electron. What's going on is I'm actually increasing the number of protons in the nucleus. I'm going to show you something for that, to show how that works in a second. And then finally, what number do I put up here for the mass number? Because this was 208, and then this is 0, so what happened here? What number goes in the mass number for my bismuth? It would stay the same. Very good. So we'll just put that number there, because electrons don't have a mass, so the mass number, or they don't have a very large mass. They don't have a mass number, I should say. So the mass number of the nucleus remains the same. Now, what the heck happened in the nucleus here? Let's actually do that over here. What ended up happening here was that a neutron, which has a charge of 0 but a mass of 1, turned into a proton and an electron. And so this is the beta particle right here. So what happened was, in the nucleus, one of the neutrons said, oh, I don't want to be a neutron anymore. So it got rid of an electron, and itself became a proton. And so in this way, the mass number, which is 1, stayed the same on both sides. And the charge number, or atomic number, which is 0, stayed the same on both sides too. So when beta radiation occurs, a neutron in the nucleus of the atom is turning into a proton and ejecting an electron. Which I'm sure sounds really bizarre. And it kind of is. Turns out that neutrons are not super stable unless they are paired with other protons and other neutrons in a nucleus. And they will decay into protons and electrons. So that's beta radiation. What we have done in both of these examples here is that we have taken the mass numbers on the top and we have made sure that they equal each other. And then we did the same thing with the atomic numbers on the bottom here. So the numbers on the top have to be equal on both sides, and the numbers on the bottom have to be equal on both sides. All of the components have to add together to make the total. Same thing down here. We have 82, and then we have 83 and -1. Those are equal. And then on the top here, I have 208, 208 plus 0, and those are equal as well. So this is how you balance nuclear reactions. And in the lab, I'm going to have some questions that ask you to do that. I'm going to give you a blank and 2 atoms, and you have to tell me which radioactive particle happened. Now up here for the last example, you'll notice that for light, not much is going to happen. If it has 0 mass and 0 charge, what happens to my nucleus? And the answer is that this is what happens. So I'm going to pick any old nucleus. So I'm going to pick this one. Just because I was looking at it. And I actually need more space here for this guy. So if I emit light, there's no change in the mass, so that stays, or the atomic number, so that stays the same. And there's no change in the mass number, so that stays the same. So why does this happen? And the answer is, some nuclei have a special state which is called metastability. And their mass number is indicated with a lowercase m after it. Now, why this happens is beyond the scope of this class. In fact, I don't actually know the answer to this. Why do metastable nuclei occur? All I can say for our knowledge is that this is something that occurs when atoms are created in a cyclotron at very, very, very high energy, and sometimes the nucleus is just not as stable as it could be. And when it does that, it may not give off an alpha or a beta particle. It may just kind of rearrange itself, move around where the neutrons are located or something like that. And when it does that, the entity that's released is a gamma ray. The take-home message for gamma radiation is that some isotopes can do this, and if you see the M after the mass number, then it is capable of gamma radiation. And that's really all you need to know for that. Now, what types of radiation are out there? There's these 3 forms, but like, how do we observe them in the world? For instance, if you live somewhere, not necessarily Western Washington, because there's not much uranium here, but if there's a lot of uranium in the ground, then what ends up happening is the uranium can actually decay into radon. Radon is a gas, but it is also radioactive. And that radon can emit alpha particles in your lungs if you've breathed it. And this is actually a very important concern if you live somewhere like, say, the Rocky Mountains, where there's lots of uranium in the ground, or maybe in the Great Plains, or even like the Appalachian Mountains. Because uranium is the sort of thing that's in the ground all the time, and it's always decaying in very small quantities. And we'll talk about half-life in a second here to show how much is decaying. But when it does that, it generates radon, and radon is also radioactive, and it can decay too. And because it's a gas, it gets everywhere. And so you may have been somewhere where like they had a radon detector that would announce the presence of high concentrations of radon. And it's important to be aware that that's a possibility because you obviously don't want to subject yourself to alpha particles in your lungs, which can cause cancer. Beta radiation is pretty uncommon. I can't think of any common sources of that. But gamma radiation is just a very high form of light. We actually use slightly lower forms of light in medicine all the time, and it's called an X-ray. So if you've ever had an X-ray, what we are doing is we are doing something similar to this, but generating a low energy photon relative to a gamma ray, called an X-ray. And the X-rays will pass through you or maybe interact with matter. And anything that passes through hits the detector and shows up as black on the screen. And anything that the X-ray interacts with and doesn't make it to the detector will show up as white. And so you can get a resolution image that way of, like, say, bones or your teeth or whatever, because your bones will absorb X-rays to some degree. So those are the forms of radiation. That's why they're important. Radiation is all around us. You should not be terrified when you hear the word radiation. That is just a fear-mongering tactic. The amount of radiation that you are exposed to on a daily basis is not zero, but it is very, very low. Accumulating a lot of radiation at once can be very dangerous. In fact, it can be deadly. And the lab documentation talks about that. It shows how much radiation a person can tolerate, and then it shows how much radiation you will get when exposed to certain sources. And you'll be surprised to find out that things like air travel, if you go flying on a plane, you are exposed to radiation because of the sun. The sun is bombarding us with radiation all the time. Most of that is just light in the visible and UV and infrared region. But high energy photons exist, and what ends up happening is that the ozone layer filters that out. But if you go flying, you fly above part of that filter, and thus anything that is high energy can pass through the exterior of the plane and then collide with you, and so you're exposed to radiation. It's a small amount. It's about 5 times the amount that you would experience normally in a day. If you went flying thousands upon thousands of times in a day, that could be dangerous. But that's actually not possible because you can't be on an airplane in multiple places at once. Likewise, if you get an x-ray at the dentist, because you got to, every like 6 months, you have to get your x-rays updated or whatever, getting 10 x-rays at a time is not terribly harmful. But if you got 50,000 or 100,000 x-rays, that could be a lot of radioactive damage that you accumulate. So it's all about exposure and time. So if you get lots and lots and lots and lots of x-rays done over a very short period of time, that could be bad. But if you get a few of them done here, and then 20 years later you get a few of them done there, and so on and so forth, it's essentially harmless, and you don't have to worry about that. All right, that's radiation and that's radioactivity. Are there any questions on that before I start talking about half-life, which is the last thing we're going to talk about before we go to the Q&A and or break and or dinner or whatever? Let me know in the chat if you have any questions about these particles and what they do. All right, the last thing we're going to talk about is the concept of half-life. So, if you play video games, you know the name Half-Life from the Valve series that's been around for like 25, 30 years. It's a very good series. It's a lot of fun. But the meaning of the term specifically refers to how long it takes samples to decay. So, for example, let's suppose that I have some radioactive substance, and we'll just put R on it. If I have 100 grams of that substance and I wait a half-life, after that period, half of it will have irradiated. And it will irradiate by whatever mechanism it does, alpha, beta, or gamma. Now, the half-life is going to be some time interval. And that time interval can be short or it can be very long. For example, uranium's half-life is 4 billion years. If I give you 100 grams of uranium today, in 4 billion years, only 50 of it will be left. What that means is that it decays pretty slow. You don't have to worry too much about being exposed to uranium radiation with a half-life of 4 billion years. Specifically, that's uranium-238. If I gave you cobalt-60, though, the half-life of that is much shorter. And that would involve a lot more radiation being exposed. So the take-home message here is that for a short half-life, You have a fast decay, and lots of alpha, beta, and gamma come out because all of the atoms are decaying much more often. If you have a long half-life, then you have a slow decay. I don't know what the heck that is. Slow decay is what I meant to say. And you have less radioactive particles that come out of that sample over a period of time. And to show that graphically, something like this, so a short half-life would be like this. It would decay very rapidly, and you'd eventually have almost nothing. But for a long half-life, it would decay much more slowly. So this would be short, and this would be long, relatively speaking. Now, for uranium, it would be really long. Uranium would almost be a vertical line going this way. In the experiment, or in the documentation that you're going to read about, you're going to watch a video where radioactive decay is simulated using straws. And so the instructor cut a straw into various pieces, and he set them all on their sides, and he put them in a box, and he shakes it. And based on the number that land on the round side, that's going to be a count of how many of them decayed. And you're going to see that the things that are more stable decay slower, and the things that are less stable decay more quickly. And that you can predict behavior of stuff based on how stable these straws are. And it's actually a really good video. I found it and I was like, wow, I have to use this. In the laboratory, what we would normally do is we'd have you do the penny experiment, which is I give you 100 pennies, you put them in a bottle and you shake them, and you dump them on the table, and then anything that's heads you throw away. And you keep doing that until you run out of pennies. And then you observe, oh, okay, every time I lost half of my pennies, so the half-life is one throw. And I feel like that's kind of a duh experiment. But with the straws, it's a lot less easy to predict. If you shake all the straws, maybe not half of them will decay. Maybe it'll be some other number. And the point is to see that it's roughly constant each time. Alright, so when you look at half-life, you will see a number. The number represents how long it takes for that sample to decay half of its sample away. When it does that, it expels radioactive particles, so that would provide radiation. Something that does that quickly has a short half-life, and that would be dangerous. Something that has a long half-life does that slowly, and thus would be less dangerous. That's all I got. That's my radiation lecture. I hope everyone feels a little more comfortable around radiation, because it's not dangerous when used appropriately. And in the workplace, we actually do use it for medical imaging and stuff like that. So don't be afraid when you see the radioactive symbol, or hear the word radiation, or hear nuclear power, because that's kind of what people have trained you to believe. It's like, it's dangerous, and in reality, if it's used properly, it's not. Alright, what I'm going to do is I'm going to put the title card up. I'm going to set the timer on screen, which I need to open. And if anybody has any questions during the break, I will be happy to address those when I get back. Or when we get back. So I'm going to start the timer now. And we'll start the music. Type any questions you'd like in the chat, and I'll answer them when we get back. If there aren't any questions, then I will adjourn the stream and we'll end that at that time. So see you in a few minutes. All right. Looks like I didn't get any questions in the chat log, so I'm going to take the stream down. Let me turn these guys up. I want to wish everybody a wonderful evening. Remember that worksheet number 4 that we talked about today will be due next week on Thursday. But quiz 6 is due this Thursday, so that is tomorrow. Make sure you get that done by the deadline. Have a wonderful evening. Stay safe, stay healthy, stay at home.